the key point is the total received signal is actually dependent on two factors. One is long-term fading, another is short-term fading. Now, when long-term fading comes due to terrain, buildings, and shadowing. Terrain means suppose some hilly area is there, and in one side some tower is there, and suppose your mobile device is kept in the terrain or it is moving through the terrain, then what will happen? Some long-term fading will take place. Suppose there is a building in your propagation area. Okay, suppose some shadowing. Shadowing means again the same thing. Like suppose you know that in our university also, in some building, the mobile signal does not reach well. Okay, so this is a long-term fading. This is a permanent kind of permanent issue. Now, if you just move out from that area, then you again get the signal. So I have experienced that in the canteen, the mobile signal is very less. So this is due to long-term fading effect. And then just you come out from that and just you open to that open garden area, then the mobile signal again comes. So then the mobile system is actually getting rid of that long-term fading effect. And short-term fading effect, that can happen anytime due to multipath propagation. So it does not depend on some specific reasons. So whenever there is some multipath signal is coming and it is cancelling each other due to destructive interference, then short-term fading takes place. Now, how should I get this local mean? So local mean means what? Mean means some average. Okay. So if I tell you that what is the average age or average height of all the students of your class, then what we will do, we will simply add the heights of all the students and divide the divided by the total number of students. So we will get the average height. But why I do the addition? Because I know that there are 30 students in your class. So 30 samples will come and I will divide by total number of samples, that is 30. But when a signal is continuously varying means it's a function of time. So I don't have any specific number of samples here. I don't know the number of samples. So for these continuous cases, an alternative technique is called integration. Okay. So first we will integrate the received signal. Received signal is RT and dt is a very small amount of time. Okay, dt. And then we integrate the value from t1 minus t to t1 plus t, because our required duration is 2t. Suppose for the duration of 2t, we want to see what is the average value. So t1 minus t and t1 plus t, it means what is the range? It means t1 plus t minus of t1 minus t. This is the full range. So full range means what? The limit becomes 2t. This is the range of time. So if we integrate this signal RT dt over a range t1 minus t to t1 plus t, it means it is actually getting integrated over this duration 2t. Now we need to divide by the total duration. So this is actually, we are making the average. Okay. So 2t means the averaging time interval and RT is the received signal. So finally we will get the local mean signal. So for example, suppose the blue line, if you look at this graph, the blue line means the instantaneous received signal. What is the signal that I am receiving at every moment, and due to some reason it is some low signal points are there, some high signal points are there. And mean signal means, if you look at this red line, see, it is just going in between the highs and lows. It is going in the middle of these highs and lows. Okay, so this signal is called the mean signal or the average signal. Okay, now when some signal is continuously coming and you want to observe the average power of that signal or average signal strength, then you need to record it for a very long duration, and then you need to integrate this and you need to divide it by the total time for which you have recorded that signal, and then you will get that local mean signal. Clear how we get the local mean signal? Now this local mean signal, so for this, in this example, we have assumed that the local mean signal is a function that is dependent on time. Okay, but also this local mean signal can be dependent upon the location of the mobile phone as well. So location means it is some distance, and this is x1, and say the averaging distance is 2l, then the equation becomes similar. Just in the place of t we will be writing l here, in the place of capital T we will be writing L here, okay, and in the place of small t1 we will be writing small x1 here. That's it, there is no other changes. So this local mean signal can be a function of the distance also. Distance means the distance of the mobile phone from the mobile tower. Okay, so this can be a function of that also, and in terms of distance we can modify the equation in this manner. So where m of x1 is the local mean at position x1, the 2l is the averaging distance, and rx is the received signal as a function of distance. Okay, so be it in terms of time or be it in terms of distance, this local mean actually represent the slowly varying part of the signal. Because already we discussed that when there is a variation of signal, one part is very slowly varying or it's a long term part, that is called local mean, and another part is very quickly varying, that is called the short term fading part. So now this local mean contributes to this slowingly varying part or some part that is taken for a very long duration. Now comes short term fading. Okay, so short term fading means if you look at this diagram, so compared to this diagram compared to this diagram, in this diagram, see, fading is happening very frequently. So you will be finding that from this local mean value, the minimas are very frequently happening. It means the destructive interferences are happening very frequently, and the signal strength is going from high to low very frequently. Why this happens? Because this is called short term fading. So short term fading, this is expressed in terms of dB when the signal strength matters. So this is actually RT minus MT. So it means short term fading is equal to instantaneous signal minus local mean signal. Clear? So if the received multipath components, why short term fading occurs? Already I have told that in multipath signals are coming from different locations, and due to the multipath effect, the signal components are getting cancelled to each other. Then the signal amplitude falls very abruptly, and it is very frequent. Okay, so the main reason for this short term fading already I have told, that is reflection, diffraction, scattering. These are the three main reasons for this short term fading. Okay, now what is the effect that we experience when short term fading comes? So we get a very poor voice quality. So sometimes suppose I am calling you, but you are not being able to hear, or my voice quality is very poor over normal telephony, not through WhatsApp call and something. So this is um, the effect of short-term fading. And if our mobile signal is very low, suppose I am being able to connect, but the call is not getting connected. So these are the direct effect of the slowly varying part. For that, the signal is low for a longer duration of time. Okay, so this is called long-term fading. So now we will discuss the experiment associated to cellular and mobile communication. So our experiments will be based on Python. So first experiment is simulation of received signal model in mobile radio environment using Python. So this will be based on whatever we have learned. So I will also sharing this manual with you. So the aim of this experiment is to simulate and analyze the received signal model in a mobile radio environment using Python. Now we can use either standalone install Python, or we can use Google Colab. So whichever is feasible to you, you can use that. So after the completion of the experiment, so you will be able to explain the received signal model used in mobile radio communication, and for that you have studied the theory, and you can clearly differentiate by looking at the signal that which one is long term fading and which one is due to short term fading. And you should be able to estimate the signal strength value of the local mean signal, and also by looking at the shape of the signals and being able to calculate the values of the mean signal, your long term fading component and short term fading component, you will be able to understand the effect of the multipath propagation effects. So we know that any signal in the real time are actually affected by long term fading. So long term fading means whenever there is some buildings, some variation of terrain, some shadowing. So shadowing means the mobile phone is not being able to a big structure, big hills, is completely big building is completely covered, the signal propagation or completely blocked, some large obstacles. And this long term fading is also called as local mean. Local mean means that m of t, that is local mean. This is also called slow fading. This is also called shadow fading, and this is also the another name is called log normal fading. So local, slow, shadow, log normal, actually the same name. And the short term fading, so short term means it happens rapidly, very quickly. It goes to some low value and again it spikes up to some high value. Okay, so frequently fading means what? Destructive interferences. So frequently destructive interferences are going on. So this is also called as fast fading, multipath fading, and there is another name that is called relay fading. So about relay fading we will further learn in detail in the next classes, but for this class just assume just that this is called as relay fading. Now the received signal model, we know that R of t, this is a total received signal at any instance of time. This is equal to m of t into r0 of t. So M of t is the local mean on long term fading component, and R0t is actually short term fading or multipath component. Now we have also the idea of calculation of local mean, that how through integration process we obtain that. I am not going into detail because already in theory class we have discussed. And for this we will be requiring Python 3, or you can use Google Colab or Jupyter Notebook. So do you know using uh, your Google Colab? I guess yes, right? So we will be executing this program in Google Colab. So the first program is simulation of receive signal model. So this is our first program. So now what we will do is, so the program is given. So I'm showing one example now. Through an assignment you will be given another problem that you need to submit separately to get marks for practical. I'm just showing how to do that. Now you will also do in the same way. So the first program is simulation of receive signal model. So this program we will be executing in Google Colab. So already I have opened the Google Colab, and we are using this Google Colab for this. Okay, so what we are doing actually, so we have taken one long term fading component or slow variation signal. Okay, so that is M of t. We have taken one function to represent the slow variation signal. We have also taken another function R0t for the fast variation or short term fading component, or I mean long term and short term. These two signal components we have taken, and this total received signal RT, we know that this is M of t into R0 of t. Okay, so we are defining R of t as M of t into R0 of t. And now what we need to do, we need to plot this RT value when MT and R0T are already given. Now we know that T means what? This is a discrete value we need to take, because whenever we want to plot something, we need to plot some fixed number of points. So we take a very large number of points, so that it becomes equivalent to some continuous wave. So that is why we are taking 1000 points. Okay, so varying from 0 to 10. So the value of t, that is varying from 0 to 10, and the number of points will be 1000. So now we are plotting these signals. AMT, the equation is already given. R0T, this is also given. So separately we will be plotting these three types of signal. Now if we execute the program, it will take some time to execute. So it's executed now. So you can see, first we get some long term fading component or MT. Okay, So very slowly it is varying. Okay. Now this is very short term component of fading. So very quickly it is varying, this short term fading component. So effectively this long term fading component is actually a low frequency signal, and the short term fading component is actually a high frequency signal. Now when we multiply these two signal, then we get this RT is equal to MT into R0T, and it is having such a form. So one thing we can understand that it is very close to amplitude modulation. Okay, because the amplitude of this high frequency signal is, you can see this is getting varied in accordance with this low frequency signal or long term fading component. Okay, so though this is not exactly amplitude modulation, because amplitude modulation equation is different. Okay, so this equation is similar but a bit different. So now you need to tell that where the equation of amplitude modulation and this fading signal actually differs. But by looking at this portion, like by looking at this portion, you can see the amplitude is varying, but the frequency is as per this high frequency signal. Okay, so anyways, through this Python program, we can get the shape of the fading signal, and if we change the equation of this long term fading component and short term fading component, then we can get the idea that then what will be the shape of this total received signal at any instance of time. Okay, so for this, I mean, from this first experiment, what we can get that if the long term fading component and short term fading component is given, then what will be the shape of the total received signal RT. Any question? Okay, so now I am going to the next part. That we need to estimate the value of local mean using moving average. So this is our next experiment. So we take this program, for execution in Google Colab. So again we have taken, if we look at, again we have taken 1000 points, and we have on MT, we have R0T. We know that this RT is equal to MT into R0T. Then from that we need to calculate the average or local mean. How to do that? So if we look at this, so the blue line is the same thing that we obtained in the last step. That is the total received signal RT is equal to MT into R0T. That is my total received signal. Now from this received signal, we have calculated the estimated local mean or MT, and it is going varying in the middle of this. So it is going through the middle of this blue line. Okay. So in this way, we can estimate the local mean signal from the received signal RT. Now in the third program, what we will do, the short-term fading component in dB. So we know that the short-term fading component R0 in dB is equal to RT in dB minus MT in dB. So this we will try to realize using Python program. So in the y-axis, we have expressed the amplitude in dB for the short-term fading component. And how we get that? So our MT was given, R0T was given, and R0 and the RT is equal to MT into R0T. We know this function as well. Now what we did, we converted these to decibel. Okay. So now how to convert to decibel? So suppose this RT, this signal is in linear scale. So what we will do to convert it to decibel, we need to do first we will do RT square. We will make the square of the signal. So RT decibel. First we need to square this signal. After that, we need to make 10 log 10 of that. So 10 log 10 of this RT square. So first we need to do RT square. So we are converting this signal to power signal RT square. Then we will do 10 log 10 of that value. So finally what is happening, this power 2 in logarithm, it gets multiplied with this constant. So 20 log base 10 to RT. Okay. In the same way, the AMDB, okay, this AMDB is also, so AMT in dB is equal to 20 log base 10 into 20 log base 10 of MT. Okay. So this is how first we convert them to decibel, and after this is converted to decibel, then we do simple subtraction here. So after subtraction, we get a variation of this amplitude. Okay. So what we have learned today? We have learned that in mobile communication, there is no point to point communication. There is always multipath communication. Whenever there is multipath communication, there are several factors: buildings, trees, hills, some sharp edges, some smooth surface, some rough surface, and they create multipath through reflection, diffraction, and scattering. Due to that, long-term fading and short-term fading, these two things occur. So long-term fading means some destructive interference that occurs very slowly, and short-term means some destructive interference that occurs very fast. At any time, the received signal is the product of this short-term variation multiplied by this long-term variation. And we also learned that what is the average or mean or the long-term variation signal. So separately we learned that how by integration process we can calculate the average or mean of that signal, and by using that, if the received signal is known in decibel, then by subtracting that mean value we can get the fast fading signal.